Hi, in this video I will show you how to get the dispersion relation for a surface plasmon polariton mode on the interface between a metal and a dielectric. So the metal here extends to infinity from the bottom and the dielectric extends to infinity from the top. This is an old textbook problem, and as you already may know that the mode supported by this interface is a TM mode, so we only have H field in this direction and the electric field in the plane of the propagation. So how to implement this in COMSOL? If we take just a cross section from this structure and go to the 2D version like this. So this is the only structure we need to simulate in COMSOL. It's basically like a rectangle with a bottom metal and a top dielectric. But as you already know, the dielectric should extend to infinity and the metal also should extend to infinity. And to emulate this in COMSOL, you have to put something like scattering boundary conditions in the top and scattering boundary conditions from the bottom as well. And of course, we cannot make just like infinite structures, so we have to truncate the dielectric height to some height HD and the metal to some height HM. And what we will use in COMSOL is to set on the left here a numeric port and make it on, so it will excite some unknown mode for us. And we set on the right hand side here a numeric port and we make it off, so it will accept whatever launched by the port on the left here. So some of you may ask, why don't we use the eigenfrequency solver? So the answer, I actually tried this one, but I found that using numeric port trick here is the best solution for these problems. What COMSOL will do, it will launch the mode here and get the wave vector for this mode and also give you the frequency of that mode, and then we can calculate the dispersion of the SPP. So for this particular problem, I will choose a dielectric as air, so it has epsilon d of 1, and I will choose some Drude permittivity for the metal given by this relation here, and the plasma frequency is around 300 terahertz, and the damping is very small, omega p divided by 100. And if you look at any textbook, you will find this easy relation for the dispersion diagram. It should be given by k naught is the wave vector in the free space. Epsilon m is the same as epsilon metal. Epsilon d is the dielectric. And as you see here from the denominator, that we have a very large KSPP when this term goes to 0. And it can go to 0 because epsilon m has a negative permittivity because it's described by Drude metal. So at frequencies below omega p, the permittivity of the metal is negative. So I draw this dispersion first using this analytical formula using MATLAB here, and what we need to get in COMSOL is this curve here, which is called SPP curve. And as you see, it extends from 0 up to some frequency. This frequency is given by the frequency at which this term goes to 0. And actually it's like 214 terahertz for this case. It's omega b divided by square root 2. This figure is just from Wikipedia to what you expect from this mode. You have some propagating mode at the interface that is mostly confined to the interface and extended in the dielectric here and propagates along this direction. So the question about what should we put the height for the HD and HM, it depends on the frequency you need to solve for. So this is a previous solution I have done, and I just need to show you what is the difference between when you solve at low frequency, something like 58 terahertz, As you see here, the surface plasmon mode extends too much into the electric space. So at least you need like from 1000 to 1004 micron. So at least you need 4 micron above the dielectric, above the metal, to make this mode propagates freely without any interface with the scattering boundary condition here. However, if you need to solve at some higher frequency, let's say 100 terahertz like this, you see now the mode doesn't extend too much into the dielectric. So in this case, you can just truncate the height of the dielectric up to 3 micron, for example. Of course, this height depends on the plasma frequency you choose. So for 300 terahertz, I found this conditions here. In fact, you can easily drive what is the best height for the dielectric based on this relation here. You can easily drive this one, but just from practical point of view, you can just keep it as very high as you want if you need to solve frequencies close to 0. And the other observation here is that in the metal, the mode doesn't extend too much in the metal, so you can choose the metal height not too large. It can be very small. So now let's move to COMSOL to simulate this structure. Let's start COMSOL. I select 2D, choose whatever EMW or EWRD, doesn't matter. Study this one, and we said that we will solve for a numeric port, and for this we choose boundary mode analysis. Keep this length unit to micrometer. First we set the parameters for the plasma frequency. It's 2 pi multiplied by 300 terahertz, and gamma, the damping, is WB divided by 100. Let's define a width for the region we will solve for. Let's say, for example, it's 0.5 micron. This region actually can be 0 or 0.0001 micron, but yeah, let's see what happens. And we need HD, the dielectric height. In this case, we need it to be very large because I decided to solve for a very, very small frequency. So, for example, 2000 micron even. Of course, it's very, very large, but yeah, let's see what happened. And the height of the metal is, we can keep it just like 250 micron. Now, what we need to do is to sweep over the frequency, and at each frequency record the surface Plasmon Polariton wave number. So we define some sweep parameter called f naught, and initially it's set to 20 terahertz. Let's go to the geometry. Have a rectangle. The width here is W, the height is HD plus HM, and the layers, we need the bottom layer to be the metallic height, so it's HM, and make sure that this is checked, so layers in the bottom, build selected. And as you see, we have this very strange shape, very thin and very tall, but we know that we have the interface at the height HM, which is 250 micron. So at 250 micron here, you should find that we have the interface. So we need to define the bottom as a metal and the top as a dielectric. Let's start by defining the dielectric. As you see it, let's just keep it for now that dielectric defined for both the top and bottom, and later I will show you how to define this bottom layer as a Drude model. Now go to the electromagnetic frequency domain. We said that we will solve for a mode with electric field in this plane, so it's in XY plane. So we don't need to bother the solver, and we can keep this just in plane vector. So it will solve only for electric field component EX and EY, and it will assume that the electric field in z direction is 0, which is true for this case. Now we need to set scattering boundary conditions for the top and bottom. We go to the top here, and the bottom, and the plane wave, keep it second order, so it gives you more accurate results. The last thing we need to do in this setup is to define the left port, which will have the excitation. So I choose port from the boundaries, and from the type of port we said that we will keep it numeric port. We copy this port, delete the boundary, and define the other port as the left port, but this time it has no excitation, it's off excitation. Now go to study. First, we have this initially defined boundary mode analysis, and it's for port 1. So we need to solve at the frequency f0 that we will later sweep, and we need to solve only for one mode, and we need to search for mode at very large wave vectors, so the effective mode index is very large, so we can keep this 5, for example, or even 6. All right. We need to do also boundary mode analysis for the right port. So I duplicate this one, and here in the port name, keep this 2. The last thing in the frequency domain, we need to solve at f0 and keep this hertz. So what are these steps mean? This step mean the first step, step 1, is a boundary mode analysis for port 1, and port 1 is the port on the left. So what it do, it goes to this port and try to find the mode that can be excited from this port and propagate with some wave vector k. The boundary mode analysis for the right port here, it also solve for the incoming port given this condition here, the metal and the dielectric, and also give the wave number k. So the frequency domain solver here, it just solve for all the fields inside this region. So again, this boundary mode analysis solve for the mode at this port, given its mode profile, its wave vector. The other one also the mode profile and wave vector, but this is off excitation, so just like absorbing boundary condition. And the third step here is f0 is solve between these two ports, so solve between this region. Now we need to sweep over the frequency f0, and initially we can set a very small frequency because I already chose very large structure, so I believe there will be no problem in 1 terahertz up to 207 terahertz at, for example, 50 points. The last thing we need to do is to define this region as a metallic region with Drude permittivity. So to do this, go to the EMW again and choose wave equation electric, select this domain only, and from the relative permittivity choose Drude Lorentz dispersion model. And as you see, it gives you a very similar expression for the Drude permittivity, but with some resonance frequency here. So we need to keep this only as 0, and the oscillator strength is this Fg. We need to keep it 1, and in the plasma frequency we keep it Wp, and in the damping keep it gamma. Epsilon infinity is already 1. We can keep it from material, so it will take the air permittivity because we already defined this one as air as well. Or you can keep it user defined and put it by yourself to be 1. So right now let's build the mesh. You see the mesh is very bad here at the interface, so we need to increase the mesh elements at the interface. So go to user controlled and duplicate this one here, and instead of entire geometry, choose boundary and select the boundary of the interface and divide this by, for example, 1000, just to give it more accuracy at the interface. Now let's compute the solution. It may take some time, and I will be back once it's done. No, now there is a problem here. It said that it couldn't find a solution for the 1 terahertz frequency, so let's try to increase this one here, keep it 5. As long as there is the convergence, after increasing the iterations, the error decrease. So this means the solver is converging. So the lower frequency we can have a solution is 5 terahertz. If you need to find the solution at 1 terahertz, you probably need to increase the dielectric height from 2000 micron, for example, to 10,000 microns, because the dependence is exponential actually. So when it's done, I will come back and see the results. Right, come back. Now it seems that the solution is already done, and you see just the convergence was very bad at first iterations, which means that at low frequencies it take so much iteration to get the correct solution, because as I told you that we need to increase the height very much, but for 5 terahertz seemed that it did it already. Now let's check the solution by checking the electric field, and yeah, that's nice. You see that we have already this mode at the interface, but it decays because we already have like non-negligible damping in time, gamma omega b divided by 100, but this is only at very high frequencies at 207. So let's check the mode at some lower frequency, for example. You see how much it extend very long above the interface, and as you go lower and lower in frequencies, you see that we need a really long structure in the dielectric, as you see here. Yeah, so let's go again to the interface and try to have some electric field distribution in EY direction to confirm that this is the SPP mode. Let's again go to some higher frequency, more higher, something like this. Let's try to animate this one. Select dynamic data extension, and let's repeat it forever. See the nature of this mode and confirm it's really, yeah, that's the SPP mode, right? Let's now draw the dispersion curve, And to do this, go to the derived values, global evaluations, and select from here at ports the propagation constant beta 1. This is equivalent to KSPP. So let's just write it in the description. And make sure from dataset you choose the parametric solutions and then evaluate this one. Plot this one. To do this, go to table graph here. And now we need to plot on the x-axis the K surface Plasmon Polariton. And on the y-axis, we need to plot the frequency. And let's do more thing that we need to normalize the frequency by terahertz to be in terahertz range. So we divide by 1e12 and let's plot this one. And as you see, this is the same as I show you in the presentation. We have pretty the same dispersion curve we obtained from analytical formula. And as you see, as we go almost to 214 supposedly, this k vector goes almost to infinity. So this confirms that we already obtained the SPP. And actually there is another way to plot this one, is to go to 1D plot group and choose global, and from global go to ports, again beta 1, keep parametric solution, make sure to use the outer solution here and plot this one. Now you see that it plots F on the x-axis and K on the y-axis. I don't know how to change this really, but maybe we can try something like this. Inner solution instead of outer solution. Still no, so I prefer to do just using this way and plot using the table graph here. Yeah, that's it for this video. If you think that you will need the model, please email me. I can share it with you. And thank you.